Good morning, everyone. Myself, Dr. Imrati Kumari. Today, we are going to discuss about vibration absorber. First, we will discuss what are the application of vibration absorber. In the figure as shown, a spring and shock absorber attached to a washing machine tub. And in figure 2, it is shown the vibration absorber in power transmission and tune mass damper in buildings. Moreover, vibration absorber used to control the vibration in transmission cables, torsional oscillation of crankshaft, rolling motion of ship, and noise in aircraft cabin. Then the types of vibration absorber. First, vibration neutralizer. Here the secondary mass is connected to primary system using a spring element. In the auxiliary mass absorber, the secondary mass is connected to the primary system by a damper or dashport. And then third one is the dynamic vibration absorber. In general case where both spring and damper are used to connect the secondary mass with the primary system is known as dynamic vibration absorber. Then the vibration neutralizer. In the figure 3A, there is a primary system. We can also call it single degree of freedom system. Here, the spring having the stiffness K1 is connected to mass M1 and we have applied excitation force F is equal to F naught sine omega t. Exciting force is acting in the downward direction, so the restoring force due to spring K1 is acting upward direction. That force is K1 x1 and the inertia force due to mass N1 is also acting in the upward direction and that is M1 x1 double dot. To convert this primary system into a vibration neutralizer, we have attached the secondary mass using a spring having stiffness K2 to the primary system and the system becomes double degree of freedom system. Here the excitation force is acting on the mass M1 in the downward direction that is F naught sine omega t. In the excitation force, F naught is the amplitude of force and omega is the excitation frequency and there is no force on the secondary spring mass system. Governing equation of motion. So first for the primary system, we are having the inertia force M1 x1 double dot that is acting on the upward direction plus the restoring force due to the spring stiffness K1 is K1 into x1 that is also acting in the upward direction equals to excitation force that we externally applied on the primary system that is F naught sine omega t. If you assume the displacement of this primary system is having the simple harmonic motion, then x1 is equal to a sine omega t or a cos omega t. It's a function of sine or cos. Using the displacement, we can calculate the acceleration and that is x1 double dot is equal to minus omega square a sine omega t by substituting the acceleration and displacement into the governing equation of motion. We will get the magnitude of displacement amplitude A that is F naught divided by m1 omega n square minus omega square. Here omega n is the natural frequency of the system that is denoted by root of k1 upon m1 and omega is the excitation of frequency of the system. When the natural frequency of the system coincides with the excitation frequency, then amplitude A is maximum and that system is called uncontrolled system. The response of amplitude versus frequency is shown in figure 4. And then there is the another curve for the control system. When we attach the secondary spring and mass to the primary system, then we will get the two natural frequencies omega n1, that is root of k1 upon m1, and omega n2, that is root of k2 upon m2. Then the governing equation of motion for the double degree system is, first we will draw a free body diagram. Here on the mass m1 we have applied the excitation force F is equal to F naught sin omega t in the downward direction, and then the restoring force due to spring K1 is acting on upward. That force is K1 x1, and the inertia force due to mass n1 also acting on the upward, and the value is m1 x1 double dot, and the restoring force due to spring K2 also acting on the upward direction, that is K2 into x1 minus x2. Then you can write this equation m1 x1 double dot plus K1 plus K2 into x1 minus K2 x2 equals to F naught sine omega t. Similarly, for the secondary mass m2, the free body diagram is shown here. On the mass m2, there is a no excitation force, but due to the excitation force on mass m1, there is a displacement x2 that is on the downward direction. So inertia force and the restoring force is acting on the upward direction. And the inertia force is m2 x2 double dot, and the restoring force due to spring K2 is K2 into x2 minus x1. So governing equation becomes this equation 2 m2 x2 double dot plus K2 into x2 minus x1 equals to 0. By rearranging the equation 1 and 2, we'll get the equation 3 in this form. Here x1 and x2 are simple harmonic motion. So x1 will be A into sine omega t and x2 will be B into sine omega t. A and B are the magnitude of the displacement. Using the equation x1 x2, we can get the acceleration at x1 double dot equals to minus omega square a sine omega t, and the acceleration for the secondary system is x2 double dot equals to minus omega square b sine omega t. By substituting the equation 4 into equation 3, we will get equation 5 as shown here. And using the equation 5, sin omega t will cancel out. You will get the amplitude magnitude of displacement A and B, that is inverse of matrix into the vector. The magnitude of displacement A for the primary system is equal to F naught into K2 minus omega square M2 divided by K1 plus K2 minus omega square M1 into K2 minus omega square M2 minus K2 square. If K2 minus omega square M2 is equal to 0, then omega square is equal to K2 upon M2, and then the amplitude A becomes 0. It means there is no vibration, and for that condition the magnitude of amplitude B will be F2 K2 divided by K1 plus K2 minus omega square M1 into K2 minus omega square M2 minus K2 square. By substituting K2 minus omega square M2 equals to 0, this amplitude of B becomes minus F1 naught divided by K2. And this is the condition of a tuned mass temp. Hence, if the vibration frequency of the primary system omega 1 is equal to root of k1 upon m1 will coincides with the secondary system, omega 2 is equal to root of K2 upon M2, then system is called tuned system. It is possible to completely eliminate the vibration of the main system by suitably designing an attached spring mass system with stiffness K2 and mass M2 such that natural frequency of secondary system coincide with the excitation frequency. So excitation frequency omega square equals to K1 upon M1 equals to K2 upon. Then the effect of vibration absorber is shown in the figure 5 here. The primary system is represented by the red curve. There is no vibration absorber, then it's uncontrolled system. When we add a simple spring and the mass to vibration absorber, there is no damping. Then the system is again, the curve is represented by purple line and the system is again uncontrolled. If we add a spring mass damper, but damping is small, then this curve is represented by the green line and that is having the vibration but within the limit. The transmissibility will be vary between 0 to 20. But if we attach a spring mass damper with optimized damping, then we will get a tuned mass damper. The vibration effect on the observer is represented by the blue curve and we get a smooth peak. So to design processor of the vibration absorber, first select the excitation frequency which will be tuned to 0 amplitude. Means omega square equals to K2 upon M2. We should select the K2 and M2 considering the restrictions, force and motion of absorber mass. Then check the mass ratio. Mu should be it should be greater than 0. Mu is the ratio of secondary mass to the primary mass should be greater than 0.05 and it should be less than 0.5.